So good morning to all of you, if I didn't already say it. So we are in integration now, and we did finish all of the last packet, correct? Anybody want to put their 2 cents in? Anyone that's in the chat that was here last time? All right, well, I guess since somebody wants to talk with me, I'm going to say I'm pretty sure we finished that last time. So I'm going to go ahead and start with, actually, let me go back and check that, because I'm not sure if we did all of the fundamental theorem of calculus. So today we're going to start with Fundamental Theorem of Calculus Part 2. And it says that if a function f is continuous on some a to b, then the function g is defined as an integral. Notice the bound is x there of a function of t. Then you get back, or if you were to differentiate g and get g prime, well then it just equals f of x. So these here want you to find the derivative of each of the functions. So that probably looks a little strange to you. So let me explain what it's trying to say. I'm actually going to write it in a little bit of a different form because that's only if the bound is x. If the bound is some function of x, well then it's a little different. So there in the packet it says g of x equals a function of t dt integrated from a, and I'm going to change this to h of x. So that if I differentiate g, which means I'm taking the derivative of this integral, what I will get back is this function with x plugged in, but I will also get this function here's derivative. So if this function is just x, well then the derivative of x is 1, and this still follows what's given there in the packet. So the first question gives us g of x equals integral 1 to x and then it's the cubed root of t squared minus e to the t dt. So what we would get out of this is this function with x plugged in times the derivative of whatever this bound is. Now that bound is x, so the derivative of x is 1. So we're done. It is literally that simple. I want to jump to C first. I'm going to integrate it, then differentiate it, and then use this rule so that it might make more sense. So it's the integral of 1 to x squared of 1 over 2t dt. Okay, so I'm actually going to do the integral. I didn't do it for the one prior because we don't know how to solve that yet. This one we can do, right? I can pull the 1/2 out. And then I've got the integral of 1 over t dt. That is natural log of t. Evaluated from 1 to x squared. So this is 1/2 natural log of x squared minus natural log of 1. Natural log of 1 being 0. So that's my g of x. So if I want g prime, well, to take the derivative of the natural log, right, I get 1 over the inside. Still got this 1/2 out front, times the derivative of the inside. So that's what the answer should look like. So I've integrated and then differentiated. Now let's use this rule to prove that it's true. It says that we're going to get this function with x plugged in times the derivative of that function that's the bound. Oops. No, sorry, in this case, because it's x squared, we plug in x squared. Or we plug in whatever that function is. I should have wrote that here. This is f of each of x. So I should have been saying with the bound plugged in, not with x plugged in. Sorry about that. And that gives us the same thing once again. So hopefully that proves to you that this rule is predetermined. And you can do it both ways. But of course there's no sense in doing the integration then differentiating if you can just use this shortcut. So this is a nice little formula that we get because of the fundamental theorem of calculus, which basically is, well, the fundamental theorem is just the integral equaling its antiderivatives, but the idea behind the whole thing is that you get the derivative of an integral or integral of a derivative that cancel one another. Alright, let's do the other two. So B says and I'm just going to call it g of x again. Doesn't matter what it's called, just so we don't get confused with all my functions here. Integral 1 to x, and the function inside is sine v over 2 plus v squared dv, or v to the fourth, sorry. So again, right now we have no tools to be able to solve this. So the only way we could do this possibly is with the fundamental theorem. And it's only possible because my bound is x and the integral is a function of a different variable. Right, notice this is x and this is t, so they can't be the same variable to start. So g prime, derivative of this guy, right, the function that is the bound is just 1. So all I really need to do is just plug that bound into this guy everywhere I see a v. And that's it. Again, it's seems kind of silly, but it's actually a pretty powerful tool. All right, and the last one here is integral from 1 to sine. And actually, let's do this, just because you may have a question about it. So let's just change it here. Let's start at sine and go to 1. And then let's have 1 over square root 1 minus a squared dA. Okay. So I just put the bound down here instead, because I want to show you what happens if the top bound is normal and the bottom bound is a function of x. So g prime, I'm going to take that, plug it in anywhere I see a into the function. So a is sine in this case then, and sine squared is what we get out of that. Then we need to multiply by the derivative of the bound, which is sine. So the derivative of sine is cosine. And the last thing that we need is a minus sign. Right, the reason we get a minus is because it's the lower bounds. Remember that we subtract the lower bound. So that's the only difference if sine was the top bound, or in this case, the bottom bound. And you could have both bounds being functions, and then you would have a combination of one minus the other one over there. So we're just left with minus cosine, and then 1 minus sine squared, you should know, is equal to cosine squared. Square root of cosine squared is also cosine. So this one's really nice. It comes out as minus 1. Any questions about those problems before I move on? Alright, so it doesn't look like you guys have any questions, so I'm going to go ahead and continue. The next topic is the indefinite integral. And what's different from that and what we've done so far? Well, the definite integral is when we have bounds on the integral, right? When we have to plug in numbers for x. And indefinite means there are no bounds. And the only difference is that when we integrate at the very end, instead of plugging in numbers, we need to put plus c. And that c is called the constant of integration. And it represents just some number that we would get if we had numbers to plug in. So it's written formally as the integral little f of x dx equals its antiderivative plus c. So these are exactly the same type of problems we were doing before. We just don't have to plug numbers in. So the first one is cosine of x plus e to the x plus 3x squared. All of that with respect to x. So I need to integrate each one of these with respect to x. I could break it up into 3 separate parts, each integral giving me a separate c, so I'll do that the first time, and then we'll see why that's not needed. So this is really the integral of cosine plus the integral of e to the x plus the integral of 3x squared. And I'm going to go ahead and throw this 3 out front. So integral of cosine is what? You guys tell me. See how many of these you remember. So good. Sine x. And I'm going to say plus c1 for that one. Integral e to the x. We love that one because it's just e to the x. Plus c2. And integral of x squared is x cubed over 3.
I found these results.
Okay, Google, thank you. I don't know what I asked you for.
Sorry, I don't know how to help with that. Here are other things you can try.
All right. So this simplifies, and we've got all 3 of these constants. So if I add, if this was 2, 5, and 7, if I add them all up, I get another constant, right? So I could make this sine x plus e to the x plus x cubed plus c. So yeah, you would technically get a constant out of each one, but because they're all constants, you can add them all up to get a new constant and just call it plus c. So again, that's the only difference. We go from here to having a plus c. All right, so let's do B. integral 1 over x plus 7 over x to the 15th minus 6 over x squared dx. So before I integrate anything, I'm going to rewrite these second two being careful not to rewrite the first one. Right, that is natural log. These two I have to write as negative powers. So this is natural log. I add 1 to the power and divide by the number. And then same thing here. Add 1, divide by the number, and then plus c. So let's simplify. 7 over negative 14 is minus 1/2, but I'm going to put this back in the denominator. Negative and negative makes this positive. 6 stays on top. That x goes back in the denominator. All right. Part C has integral square root of x 1 over square root of x is 5 over the 3rd root of x to the 5th dx. So again, rewrite them all first. So square root becomes positive 1/2. This one here is going to be minus 1/2 because it's in the denominator. And then finally, this one's going to be x to the minus 5/3. Again, add 1 to the power, so x to the 1/2 plus 1, that's 3/2. Divide by that number. X to the 1/2, add 1. Well, it's negative, so it becomes positive 1/2. Divided by 1/2. And this one here, add 1 to that would be negative 2/3. Divide by negative 2/3. And of course, we need a plus c. So instead of dividing by these fractions, let's multiply by the reciprocals. And because everything was radicals to begin with, let's rewrite them that way. So this is going to be 2/3. This is going to be the square root of x cubed. Then we've got 2 times the square root of x. So we really don't need this. And finally, negative and negative, this makes positive. I'd multiply by 3/2, so that becomes 15 over 2 and that x goes back in the denominator, and it's the third root of x squared, and then plus c. Everybody doing okay so far? D, I'm going to skip. And we can come back to it after we learn substitution, because I think I put that one in here by accident. So let's go ahead and do E and F. So integral 3x to the fifth plus 6x minus 1 all over 6x dx. I would suggest breaking this into 3 integrals, or at least 3 fractions. So this is going to reduce to x to the fourth over 2. All right, one of the x's cancel, and 3 over 6 becomes 1/2. That's obviously 1, and minus 1 over 6x dx. Integrating, right, integral of x to the fourth, that becomes x to the fifth. We divide by 5, but there's already a 2 down there, so we just multiply the two numbers. Integral of 1 is just x, and this is the integral of 1 over x. That is the natural log. So the 1/6 comes out in front. Natural log x. All right. If you guys have questions, please ask. Alright, got the integral of x squared minus 3x minus 4 all over x minus 4 dx. So can we factor the top here, the numerator? So I would need two numbers that multiply to -4 and add to -3. So I think -4 and +1. check. That's x squared plus x minus 4x, that's minus 3x minus 4. That looks good. That means I can get rid of those. And now I just have the integral of x plus 1 dx. And that's easy. That's x squared over 2 plus x plus c. So any questions about any of those problems, guys? How did I actually integrate, you mean? So integral of x, right, you add 1 to the power and divide by the number, so it's x to the first. So that becomes x squared over 2. Integral of 1 dx is just integral dx, which is x, and then plus a constant. Right, it doesn't matter that I have parentheses around those. You could just drop them if you wanted to make it 2 separate integrals. Is that what you meant by last part? Yep, no problem. So we've only got a couple more problems here in this packet, and then we can call it an early day if you like, and we can start substitution next time. So there are very specific rules for integrals, and there are 5 of them given here. I'm just going to go ahead and put up the page on your screen so you can see it and we can just talk through it. Excuse me. Alright, so you should be able to see the rules there. So the first one says the integral from a to a. So that should make sense to you that that's 0, and here's the reason why. Right, if I've got a curve, I don't care what it looks like, and this is a. Remember that the integral represents the area under the curve. Well, if I try to integrate over a single point, I'm not picking up any area. So that should very clearly be 0. Excuse me. Then the second rule there says if I start from A to B and instead I flip the bounds and go from B to A, I must introduce a minus sign in front. So once in a while, you'll see, and this will probably be a little later in your, what we call your college career, that you'll have integrals that are the same as another integral in your problem. The bounds are backwards. So if you flip the bounds, you can introduce a minus sign. You can actually put the two integrals together, things like that. So that's mostly where that comes in handy. The third and fourth are really nice when you get to something called Fourier series. So it says here that if you have an odd function and you go from negative a to a, you get 0. So let's think about that. So here's a graph. What does an odd function look like? Well, sine is an odd function. So let's say this is a, and this is negative a. So if I pick up this area, and then I go and pick up this area, remembering that this is positive area, and this is negative area, then I should get a total of 0 out of that, right? So that's why that rule works, right? If I go from minus a to a of some function, I get 0. And if I take an even function from minus a to a, notice it says I can change that integral as 2 times an integral from 0 to a. So why does that work? Well, again, what kind of function is an even function? Well, I happen to know that cosine is even. Oops. Right, cosine looking like this. This being a and this being minus a. So those two sides are equal. So I could just integrate from this side over and do it 2 times. And then finally, that fifth rule there says that if I've got some integral from a to b, and it should say that my function is continuous, right, so I don't care what the function looks like. This could be a, this could be b. There'll be some point c somewhere in between a and b, and I can integrate from a to c and then from c to b and add those two together, and the sum of those two integrals is the same as the integral from a to b. So let's try these couple problems here. The first one says evaluate this integral from -1 to 1. So I'm going to use the fact that some of these are even and some of them are odd. Right, so the first two are, or first three are all odd functions. Right, they're odd powered or sine functions, and the last one is an even function. So this is -1 to 1 of 4x plus sine x plus x cubed dx plus another integral from -1 to 1 of 3x squared dx. So if we go back to the rules, it says odd functions from -1 to 1 is going to be 0. So this whole guy right here is 0. And the second one there, I can change from negative 1 to 1, I could do 2 times from 0 to 1. So that's 2 times, and that would be 3x cubed over 3. 3's would cancel. Don't have a constant. Come on, get rid of it. Thank you. From 0 to 1. And so this would be 2 times 1 cubed, or just 2. The second one's really easy. It's the integral from 2 to 2. So if I try to integrate anything, right, I don't care if it's even or odd, from a to a, right, I get 0. So we can very quickly jump to 0 on that one. All right, so I think I'll do 3 and 4. And I will leave 5 for you to do as part of your quiz. So problem 3 says we've got an integral from 3 to 10, and we have a number for it. We've also got an integral from 3 to 7, and we have a number for that. What's the value from 7 to 10? So this is using that idea that we can break up integrals. So our extreme bounds are 3 to 10. So the integral from 3 to 10 of this function has to equal the integral from 3 to 7 plus the integral from 7 to 10. So now just plug in the numbers. So from 3 to 10 it was 25. From 3 to 7 it was 20. And let's just call this I for the integral. So it should be pretty clear that I equals 5. Everybody okay so far? All right. Okay, great. So number 4, again, we've got an integral from 2 to 4. Then we've got one from 0 to 2. And then we've got one from 0 to 4. So still the extreme bounds are 0 and 4. But remember, we want, and so if we want to, we can rewrite that one, right, from 0 to 4, we can go this way. And that would have to equal the integral from 0 to 2 plus the integral from 2 to 4. So we're going to solve for 0 to 4 and then recall that this is equal to minus that answer. Because if we flip the bounds, we get a negative in front. So again, plugging in the numbers, this here is 2.14. This thing that we're looking for, again, I'm just going to call I. And 0 to 2 is 8.75. So I equals, let's see, that's 8, 9, 10.89. But again, that's from 0 to 4, and we want from 4 to 0. So our answer is negative 10.89. So this one's similar to those. I want you guys to do that one for your quiz. And I think we have some integration problems as well, so just add that onto the quiz. Or maybe I can do that for you real quick. So let's do copy. Go back here and turn off that screen share so it's not driving you nuts. Let me open up your quiz. That was interesting. Copied it like an image. Alright, well, there's a box around it that I can't get rid of, apparently. Alright, so I will put up that quiz for you. Do you have any questions for me? And that is our last quiz, guys, so that you should be happy to know that. I might make one more for you if you like, just to help make sure that you're on the right track when it comes to substitution. So I probably will do that, but this is the last scheduled quiz.